suppose that the energy of an electron in an atom is quantized. It can only have this much energy or this much energy or this much energy, which corresponds to distance from a neutron. It could be this distance or this distance or that distance. You label those n, n equals 1, 2, 3, etc. And we were able to do some calculations. We were able to figure out when an electron makes a transition between these allowed distances from the nucleus. We talked about how one way that an electron can make that transition to go up in n, higher energy, is to absorb a photon. Or if it goes down in energy, goes from a higher n to a lower n, it can release energy, it can convert the difference in energy into a photon, whose wavelength corresponds to the energy of the difference in energies of the electrons. Is that all that stuff clear last time? Pretty much.
It's pretty good.
I mean, I just want to maybe I'll summarize that. See if it is clear or not.
That's pen timer. If you can do, ask me. I have a couple of them.
Yeah, you have a pen?
Do you need one?
Yeah. Bro, my pen's still. Yeah, give me one.
You got which one?
I have that one. Let's just keep this one.
Whatever works for you.
I'm keeping this.
Okay.
Yeah. I don't know. Ask him.
So did you guys get all that last time?
How does an electron just emit a photon?
It can, the energy, the difference, okay, so conservation of energy, right? We know it has higher energy in the higher and lower energy in the lower end. So when it moves from higher end to lower end, it has less energy. The energy has to go somewhere. And it ends up that one of the places that energy can go into is to create the photon.
Just can't. What was the next photon?
Photon of light.
A photon is electromagnetic radiation, which basically is energy, right?
Yeah.
So it's just like, think about it, okay, everybody seems comfortable with converting potential energy into kinetic energy, right? Just a different form of energy.
I'm just wondering about like the mechanics, but
Mechanics of it? Can you explain the mechanics of this? So in this class, we kind of just go over it.
The electron can absorb a photon if, is that
If and only if, right?
if and, oh, if and only if, okay. It threw me off pretty shorthand.
What do you mean when you say the energy has to match it on two different orbits?
Which one?
The second part?
The difference in energy of the electron in two different orbits. So if this is talking about
Oh, I see what
absorption.
you mean.
So
You
if the
mean the
electron
required amount of energy.
the difference in energy between the electron here and here is some value. The only way that this electron can absorb a photon is if that photon's energy is equal to the difference in energy of the electron in, say, this orbit and this orbit, or this orbit and any other orbit.
Okay, so it's one specific amount of energy then.
Right. So in other words, okay, so this, everybody agree that this difference here basically corresponds to a certain amount of energy. The electron has a certain amount of energy here and a certain amount of energy here, right? And we said, you guys seem to agree with this, that the electron couldn't exist, I mean, you went along with it anyway, that's what Bohr said. The electron can't exist anywhere in between these two, it's either here or here, right? So that means that it can't have this much energy. And so if the photon that is impinging upon this atom, if the energy of it is equal to, say, this much energy, it's just going to pass through. It's going to be, it's not going to absorb that photon. The only time a photon can be absorbed is if the energy of that photon corresponds to a difference in energy between the electrons in two different orbits.
Correspond exactly.
Well, we're not going to, pretty close. There's some wiggle room there, but we'll say exactly.
Is that off or if or double up?
If and only if.
If and only if.
He just asked like 2 minutes ago. That's what I just asked.
Guys, sharing the rest of this okay? This is pretty much what I wanted you to get from the journal. Then when we went from Bohr goes to de Broglie. You guys remember de Broglie?
He's that important guy.
Yeah, there you go. Wave particle duality.
De Broglie wavelength.
Remember the equation, right? Wavelength equals h over mu, right? And that relates wavelength properties, the wavelength, and particle-like properties, the velocity. So what it says is that particle can act like a wave, the wave can act like a particle. Remember that one? We did a calculation, I think, at the end. That was the very last thing we did. Next, comes Heisenberg. That is uncertainty approach. What Heisenberg said. Yes. In one dimension. He said it in 3 dimensions too, but it doesn't matter. Delta X here stands for the uncertainty in position of an object. And this is the uncertainty in the momentum. Or if we're talking about a particle with mass m, write it like this. When Heisenberg came up with his principle, one of the things he was trying to explain was the electron in the atom, how it could act like a wave. Because definitely an electron can act like a particle, we do that. They mention an experiment by Davidson and Germer that showed that electrons act as waves too. Basically, they were able to get, by shooting a beam of electrons at a grating of gold foil, they were able to get a diffraction pattern. Remember we talked about diffraction pattern, constructive and destructive interference? I talked about it with water waves. Talked about it, well, he was able to get the same thing with electrons. And that is definitely a wave-like property. So they're pretty confident that an electron can act as wave. When he came up with this, okay, what this says, okay, this is Planck's constant still, 6.626 times 10 to the negative 34 kiloseconds, 4.5. What it says is that if you one way of looking at it, let's look at this one. This is probably more useful to us. If we know the position of a particle, let's say an electron in an atom, we know it really, really well. That means the uncertainty is going to be really, really small. What that means then is as this gets smaller, the uncertainty in the position, we get more and more certain of where it is, you know less and less about its velocity. Because this puts a lower limit. Now it doesn't mean, notice this is greater than or equal to it. When we multiply the uncertainties in the position and the velocity, they have to be bigger than this number here. Now this is a really small number, right? Negative 30, so then times 10 to the negative 34 on top, right? So this is a really small number. But it's not zero, and that's the point. And what that means is that you never know, both of these exactly for a trend. So we can do it. We can use this. So, what we're gonna do here, so the problem, right? These are more or less fairly realistic numbers. We have an electron in an atom, and we're told that its velocity is 5.34 times 10 to the 6th meters per second, plus or minus 1%. And we want to calculate the minimum uncertainty in its position. So we're going to use this equation here.
Is m the mass of the electron?
Yes, it is. Well, it's the mass, in Heisenberg's equation, it's the mass of whatever object you're talking about.
But so in this
In
question,
this-
it'd be electron.
In this problem, it's the electron mass.
So if there's anything else, you can give us the number.
We gotta start making our study cards. I don't cheat sheet cards.
I have to tell you, but you guys know the mass of electrons.
I don't wanna wait till the last day to do it.
Yeah. I'm already
So,
putting
first of
memorized
all-
stuff, you know?
Yeah, that's what I'm
Which
doing.
variable are we going to
So when I
solve?
take notes, I usually
Velocity.
like one of these little bubbles and put memorize in there, and I put that stuff in my note card.
Yeah, I thought the same thing too. Just don't tomorrow. No, take your germs. I didn't even drink it. I didn't even drink it. Oh.
And what is that mass? You guys remember?
9.11, 9.109.
9.19 times what?
10 to the
Times 10 to
negative
the
31.
10 to the negative 34. So we want to make sure that the mass is in
Negative
kilograms.
31, bro.
Because remember, joules.
He's talking about
basically
electron
is
mass of an
joules, how do you
electron.
write?
Kilogram.
Sure, it's 34?
Kilograms, meters squared.
I thought it was negative 31.
I think that's something else.
No, you sure?
Yeah.
Negative 31.
Did he say 31? That's 31?
Yeah, it is 31.
Oh.
And what do we put in?
I told you it was 31.
Nah, you're right. I think it's 34. Never mind.
What's the other number?
102?
You're already given that number.
Not times 2.
Isn't it the maximum minus minimum of the uncertainty?
Hey, how the hell he gets the
When
number?
it's right, oh, plus or minus 1%, yeah.
Dun, 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 dun.
Da, 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 da.
Why is it? Because it's kilograms? Yes, negative 28 grams, right? Yeah.
So if you use mass in this equation, you want to use kilograms?
Yes. And the reason is because of the joules.
So what's the next number again? I think it's supposed to be 5 point whatever. That's velocity in seconds, isn't it? So it should be 5.34. The last number in the
I
parentheses.
agree with you, Rob. 2 times it. I'll explain that. Your book doesn't do it that way. But I agree, you're right. So first of all, how to get the number. 1% of 5.34 times 10 to the 6th, that's the uncertainty, not 5.34 times 10 to the 6th. That's the velocity itself. What you want to put in here is the uncertainty, that's the delta, right? You get that? You guys get that? So 1% of 5.34 times 10 to the 6th is 5.34 times 10 to the 4th. And if that's not clear, let me show you why. 1% is 1 over 100, right? And that's 5.24 times 10 to the 4th. Is that okay? So that's the uncertainty, and it's I told you that it's plus or minus, so it's plus this much or minus this much. So the total uncertainty is this much that way and this much that way. You guys buy that? That's why there's 2, right? So that's why this 2 is here, because it's that we're uncertain minus this much and we're uncertain plus this much. There's some frowns. Let me
I'm confused by the
Let's
two.
say this is
Plus or minus? The difference in plus or minus? Because it'd be two difference.
whatever this number here, this is the
Because it's
velocity.
either back one or forward one. That's
Look
two.
up there.
The uncertainty is,
See,
okay, so the velocity is 5.34 times 10 to the 6, 34 times 10 to the 4th. So it's plus this much. And it's minus this much.
That I understand.
yeah,
So the total uncertainty
that's two.
is 2 times 5.34
You see in the middle?
times 10 to the 4th.
If I was to draw it out, it'll look something like this. You know how you have 0, then you have positive, but here negative that way. So if you go positive, that's 1. You go negative, that's 1. And then when you put them together plus or minus, it becomes 2.
Say that again?
That makes more sense. Thank you.
That
See,
was
that's
such
just trying to explain to you, man. Sorry if my words didn't make any sense.
Man, I should be a teacher.
No, it becomes, this is plus, so it's this number plus that much, right?
Uh-huh.
It's this number minus that much.
That makes more sense.
Okay, so,
Why couldn't you just use simple words? You just put in the numbers.
Yeah, if you would have said, like you said, 0, then that make more sense.
When you explain it like that, it's like you have to know your algebra already. And where's getting that number from? 5 million? What?
so it's 5,340,000 meters per second plus or minus 53,000.
That's some change in position.
You guys,
Get my calculator. Oh my dear. I got this.
All right, Broloff,
do you see it now?
do your thing.
Yeah, that's right. We divide by
It is
100.
34.
Yeah.
I told you. No, I confused 34 from.
Talking about Planck's constant?
Yeah,
It is
right.
34.
That's right.
Mass of electron is negative 31.
yeah.
You have to be careful about how the
That's
problem
right.
is
You
stated.
made the mistake.
And I'm a little bit worried because your textbook, I noticed, they didn't do they don't include the 2. So, but no, that Ramel's right. That's correct. So yeah, you have to be careful on the wording. If it's plus or minus, then it's going to be times 2.
How did the textbook do it?
They didn't put the 2 in there.
You still got the right answer though?
What?
Did they still get the right answer?
No.
Oh.
They got just do it 2 days. What's that? Because it's this much this
I
way
can't believe it.
and this much this way.
There was a kid that beat the book.
So if we by chance on a test had something like this and we went with
I
the
write the
textbook?
tests.
I know.
Too. Yeah.
Okay.
Yes, I promise you. Okay. But one of the wrong answers might be without the 2. What do you get without the 2?
Now you're just confusing.
Why do you add, the 2 together?
I'm sorry.
Why do you add the 2 together?
Let me do this with different numbers that aren't so awkward.
0, 1, and 2. Use those numbers. Negative 1.
I was gonna say let's finish that one.
Negative 1, 0, 1. That's the easiest way to explain it.
This one actually makes some sense, yeah.
Did you get how I explained with the
The
negative?
magnitude one is the massive electron. That makes sense. You have to memorize the massive electron. No, that's proton. It's less than. It's like if it was. Electrons are actually so less. Plus or minus 5%. It's still 2.
Yeah, it'll still be 2, because yeah, plus and minus. But the only thing that changes is the percent. Like, you know how you did that 1 over 100? Like that? It's
Okay.
5 over 100.
So if you guys listen for a minute, it might help. Let's say we're doing the uncertainty in a position instead of velocity. It works the same way, right? Let's say you're told that some object was moving at was at 100 meters. That was his position, plus or minus 1%. So if we're looking at this here, let's say there is 0, there's 100 meters. So 100 meters. But we don't know it exactly is 100 meters. We know it's at 100 meters plus or minus 1% of 100. 1% of 100 is what?
1.
So
So
it's,
that must be the speed.
I'm going to expand this.
Speed is
Let's
2.9979.
say
Yep.
plus 1
Times
meter
10 to the 8
this way,
milliseconds. Meter
minus
seconds.
1 meter this way. So this gives 199 meters. So
That's the charge.
what we're saying is we know that the object is somewhere in this region right here. And so the 2, and the reason we have the plus and the minus, is that that's what that says. Plus 1% or minus 1%, somewhere in there. Is that better for you guys? No? Yes?
So, I'm going to use this because
Like that. Now I understand. She should have done it that way. It would have been much easier.
So if it was plus or minus 2%.
Put that in your notes, because you're probably gonna need it. It's right here. Okay. Extra.
No.
Extra.
The reason why is,
If it's plus or minus 2%.
okay.
The one that we use is 1.1, but instead he wants us to do up to
1% is 1 meter. Right?
So you use
That's 1 meter right there. But that's not the total uncertainty. The total uncertainty is
0.10.
here to here. So it's twice. Oh, this one's this way and here is that way.
This is the one. You only want the so equation.
Whose number are you using anyway?
Who's what?
Whose number are you going to use?
I have my own numbers, but I don't have these numbers because they got the wrong numbers for this part. So I'm going to use your numbers for this part.
Oh, okay.
But I'm going to use our numbers for this part.
Okay. So you guys sound like different then.
If it's cool with you, man.
I don't care. You can use any number. I mean, I already did it all already.
Not as well.
I know how to do. I finally understand how to do the second part.
Second part. What, this one?
Yeah. I know how many numbers
Guys,
go
you
by
can
now.
get the same number, please.
Okay.
I got 5,400. Oh wait, which one are we doing?
Oh, yeah, we're still finishing that one equation.
Oh damn, I didn't know it was the equation.
Because he didn't add in the velocity into the equation yet. 6 times with negative 34 divided by.
You guys get that? I do. Everybody else?
4.
No,
No?
no. I'm still taking my time.
I got
9.109x.
Yeah.
Since Joseph's kilogram times
Yeah, I got that number too.
Squares per second square. So the units of this look like kilograms, meters square per second square times seconds over kilograms times meters per second.
where does the second S go to?
Where's it go?
That S is squared.
What, I don't, the way, okay,
Wait a second.
look at just the.
I got 5.4 to the 12.
This cancels
You
one of
missed up.
these.
Oh.
This cancels the
That was
other.
a negative 10.
Okay.
Wait a
Kilograms cancel,
second.
this cancels one of these, we're up to meters. Sig figs,
Is it
somebody asked about?
because my numbers were wrong somewhere?
This
No,
has
your numbers
four
look-
sig figs. The
No,
four
'cause you
zigzags.
have a 6,
Pi.
flip it to the 4.
Remember when you're doing pi
no wonder.
calculations, use your calculator's pi, so that won't be the one.
Oh, I don't know why I wrote 6 up here. That's what
This
messed me
has
up.
4.
Because there was 6 in the
that's
equation.
that. This has 3.
Then why was it 4 in the...
Is 3.
Because you did 1 over 100 times that.
is meters per second, and then he put meters per second, so that should be the same. Oh, but the end he wanted meters.
So have you guys got that number now?
No, that's still. Why is there a 4 in the equation again? I mean,
Why is there a what?
the 4 on top for the. Yeah.
Yeah, 1/100.
Here?
No, he's talking
No,
about the
no,
other
never
one, the
mind.
far end.
Yeah, the last one. Never mind.
He's
Yeah.
talking about to the
Multiplied
fourth.
by 100.
Yeah, multiply 1/100.
Now, do you have to multiply it by 100?
He's talking about
Or
top.
divided by 100? Where you got the 5.3
Yeah,
to 10 to
that-
the fourth?
Because it's 1%, right? If it was some other number, you
Oh, I can. Now I get it.
So it was 2%. You do 4/100 times that, or just 2/100?
2 over 100. 2%.
2 over 100, and then you multiply by 2 again.
Oh, okay. Or can we just do 4/100?
Oh, okay, that's
You don't do 2
perfect.
times.
Okay.
Gotta write that in my little notebook here.
It's really not that bad, you just have to get used to it. This is all there is to Heisenberg's uncertainty principle for us. I mean, there's a lot.
Thank you.
We need to do another example.
All right,
No,
so
we don't.
next,
Do.
Yeah, we do.
after Heisenberg. Oh, first, let's look at the
Breaking Bad.
implications of this.
Heisenberg.
As I said, these are fairly realistic numbers, the velocity, and the mass certainly is right. So it ends up that, okay, remember I told you guys about angstroms? So this is
Yes.
about 5 angstroms, right? An angstrom is 10 to the minus 10 meters. The size of a hydrogen atom is on the order of 1 angstrom. So the minimum uncertainty in the position of an electron in the hydrogen atom is bigger than the diameter. The diameter is about 1 angstrom, a little bit less. The minimum uncertainty is bigger than the size of the atom, then that means we basically have no idea where that electron is in the atom. See, yeah, and so now where this led, okay, after Heisenberg figured this out, this led to Schrodinger, actually to a bunch of people trying to come up with a electron. And there are other
Whoa, good
down there,
catch.
but Schrodinger was the guy that came up with the equation.
Fat stand. Sketchers. Oh, cool.
Schrodinger's equation. Schrodinger equation.
I think I look at it and be like, look, it dropped. Oh, this guy, I hate this guy. It's that stupid big old white thing, remember?
What?
It's that big old white thing. Yeah, that thing right there.
Yep, it is.
The hell, I hate
The skulls?
Yeah.
And what Schrodinger did is he came up with a wave equation to describe the electron in the atom, called Schrodinger's equation. And there it is right there. It looks simple, right?
Hell no, it's not.
What? Like what?
Simple to a doctor like you,
It's a
man.
simple fork.
So I see
I see.
Hermes and Poseidon equal.
So there each of these symbols stands for something. H is what's called an operator, a Hamiltonian operator, and it has a bunch of, calculus operators inside of it, right? Like derivatives and partial derivatives and stuff. Psi, that little wavy kind of thing, the Greek letter psi, it stands for what we call a wave function. And I'll talk a little bit about that in a second. And E is the energy operator. And this is psi, yes.
Do we need to memorize this?
Is it going to be on the test?
Yes. Yes.
That's more my question.
The reason that I even throw it up there is because it makes sense to where we're going with this. I'm going to throw some numbers out at you, some numbers, called quantum numbers. And this is, I just want to be able to say this is where they came from. That's it.
You should just toss it at us. Don't throw it at us.
Horrible, man.
So,
H?
that's
How do we read
Schrodinger's
it?
equation. And what we got, one of the many things we got from Schrodinger's equation is that it can describe an electron in an atom, describe the energy, and it can describe the region of space it ends up, where that electron has a probability, a certain probability of existing. That's the only thing, we can say. Knowing Heisenberg's uncertainty principle, we know we can't point to an electron in an atom and say it's right here. But what we can do with Schrodinger is we can say that, well, with, say, a 90% probability, that electron is going to be in this region of space around the nucleus. And again, this is just so I can refer back to it.
Do you put parentheses around your numbers? No, where's this big number come from?
No, because this is what I multiply all that together.
No, just put in the whole number itself, like 4 pi, parentheses times that, parentheses
And
times
again,
2.
you're not going to actually put any numbers in for psi squared.
No,
But
put this
this
divided
is
by
leading up to
this
something.
whole part. Don't do
This is the absolute value of psi squared. The psi squared absolute value. What that is that's proportional to the probability of finding an electron in an atom in a region of space. So the value of the absolute value of psi squared gives us a probability. And if we were to look at, we're not going to, but if we were to look at the actual form of the wave function, psi. Actually, I should break that down, because I'm going to talk about wave functions, and I want you to know what I mean. Proportional to.
Giving me joy.
Nah, Batman.
Wait, as I started to say, when you look at the form of psi, wave function, it's a function. It has trigonometric functions inside of it. It also has these numbers. Okay? We call them quantum numbers. And one of the nice things, one of the really useful things we got from Schrodinger's equation is that these quantum numbers are like coordinates in a coordinate system, like x, y, and z in a Cartesian coordinate system. Well, these quantum numbers we get describe the region of space where there's a 90% probability of finding electrons. So it describes a region of space. There's 4 of them. I'm going to start out by talking about 3. So 3 of those quantum numbers, n, l, and m sub l, describe what we call an orbital. And an orbital is a region of space, a volume of space where there's a given probability of finding an electron in an atom. the word orbital to distinguish it from the word orbit, which Bohr used, right? So it's not an orbital. An orbit is a defined, it's a distinct path. It's you know, we can't use that because then we know exactly where the electron is. We can't, we're not allowed to. So again, this is where these quantum numbers come from. And it ends up that that only certain values of these quantum numbers give solutions.
Yeah, it's okay. I'll
to
look at it
Schrödinger's
later.
equation. What that means, what that translates into,
The numbers
is
from
that
the
these quantum numbers can only have certain values. They're quantized when they're described in electron dynamics. And I'm going to give you rules for what they
Thank you, Sam.
can be, and also what each of these quantum numbers describes. And
Thank you very much, man. That's all I need.
I'm talking about this part. You get right out.
so this is n, which is called the principal quantum number. And n describes the size of the orbital. That is how far from the nucleus that orbital can extend. Now, when we change the probability, like so, we're going to keep throughout this whole discussion, okay, we're talking about probabilities of finding the electron. We're going to keep that probability at 90%. If we change that, that changes how far out from the nucleus an orbital can extend. But we're keeping it at 90%. So keeping that at 90%, as you increase n, the value of n, you're talking about the electron being able to extend farther and farther from the nucleus. R is how far from the nucleus. The shell is the name of, well, all electrons that have the same value of n are said to be in the same shell in that atom. Right? So the values that n can have are any positive integer, starting with 1, 1, 2, 3, 4, out to infinity. The next quantum number, L. So these rules, this is the rule for what n can be. The rules for what values these quantum numbers can have are hierarchical. You have to know what n is first. Once you know what n is, that puts the limit on what L can be. L limit on n can go. as we,
That sounds so cool. As a me though.
so what L does, the value of L determines what shape an orbital has.
That's cool as me. As a me
So L describes the shape. We'll look at those shapes in a second. And it's the L is the subshell. So if two electrons from the same atom with the same N and the same L, then they're going to be the same subshell. And the rule for what L can be, it also has to be a positive integer starting with 0, but the maximum that it can be is N minus 1. So let's say N is equal to 3. Then the values that L could have are 0, 1, and 2. It's then not just 2, it can be anything up to and including 1 less than N. We have names for some of the most common values of L that we use. Actually, let me put it over here. Just shorthand, right? We call it an S subshell or a P subshell or a D subshell or X subshell. And we won't need to ever go past F subshells. Some people deal with those, but they're weird. And they just go alphabetically after F, G, H, I, like
SP1, SP2, SP3, SP4,
that. N, L, M is L.
But if it goes back to P again,
I'm pretty sure you see SP1.
H, I, J, K, and D, all that was P.
I'm pretty sure it was SP1, SP2, SP3, SP4. Just get me like that, like old times.
Oh, but they still got me out. It's periodic too.
I know. ML. I was just talking about the, talking about how smart he is.
basically, it picks out an orbital for us. But it works like this. It's the magnetic quantum number, and it describes which, the orientation of an orbital. Once you see the pictures of these orbitals, you'll maybe have a clearer picture of what I mean by orientation. And however many values M sub L can have that's equal to the number of orbitals that are already given the subshell. The rule is well, first of all, the values that M sub L can have depend upon what value L has. The rule is that whatever value L has, M sub L can be negative L, all integers up through 0, up to positive L. So let's say L is equal to 2, then M sub L can be minus 2, minus 1, 0, 1, and 2. So L equals 2 is the D subshell, and we just saw, for instance, in the D subshell, that there are 5 values that M sub L can have. What that tells us is that in any D subshell, there are 5 orbitals, 5 different orbitals with different orientations. See how that works? Actually, let me take a step back and walk us through the beginning. So we've already picked N. We're not going to worry about what N is now. We're just going to look at L and M sub L. If L is equal to 0, if it's an S subshell, what values can M sub L have?
0.
Only 0. Has one value, which means that in any S subshell, that is when L equals 0, M sub L has one value. There's only one orbital in any given S subshell. Okay? When L equals 1 in a P subshell, what values can M sub L have?
Minus 1, 0,
Minus 1, 0, and plus 1. That is, it can have 3 values, and that means that in any given P subshell, there are 3 different P orbitals, we say.
Sorry, right there.
You guys follow that? Then the next one we did, when L equals 2, when it's a D subshell, the possible values for M sub L are negative 2, negative 1, 0, 1, and 2. 5 different values. That means in a D subshell, in any D subshell, there are 5 different D orbitals with different orientations. And then the last one, F. In an F subshell, L equals 3. The possible values for M sub L are negative 3, negative 2, negative 1, 0, 1, 2, and 3. 7. There are 7 orbitals in any given F subshell. That's what that tells us. Now, we're never going to worry about the actual orientation. Is it pointing on the x-axis or the y-axis or something else? So we don't really care what the actual value of M sub L is. What we really care about is what values it can have, and that tells us how many values it can have, which tells us how many orbitals in a given subshell. You guys follow all that?
A little bit.
That's a big one. All right. Next, the 4th quantum number. Okay, so what these 3 quantum numbers do for us, N, L, and M sub L?
So with M sub L, the main point we're trying to get across is that it helps us estimate how many subshells there are in 4L.
How many orbitals in a given subshell?
Versus the actual value.
Right, that's right, yeah. So these 3 quantum numbers that I just described, N, L, and M sub L, they're like the coordinates describing where an orbital is in an atom, and thus where the electrons can be. But it's just describing a region of space. We haven't put any electrons in there. It ends up that in order to put electrons into these orbitals, which is our goal, our immediate goal, we have to talk about the 4th quantum number called the spin quantum number, M sub S.
How do you do this? How do you graph it?
Polygraph. Press Y. And then let's put 2 plus 3.
care about with M sub s is, first of all, the reason it's called spin quantum number is that an electron acts, it's not, exactly doing this, but it acts as if it were this sphere of a negative electrical charge that's spinning. And it ends up when you spin an electrical charge that it creates a magnetic field perpendicular to the direction of spin. So, and what that means is that when we have a negative charge, an electrical charge that's spinning, it also acts like a magnet. So it acts like it's an electrical entity, and it also will interact with external magnetic fields. What all that means is if we bring a magnet up close to it, it's going to act as if it's a magnet too. And just like we were talking about before, two bar magnets, for both north poles point to each other, they're going to push each other apart. If it's a north pole and a south pole, they'll attract each other. If we were to take put an electron into a magnetic field, it acts the same way. It's either attracted or repelled, and it only has two possibilities. It's either repelled or attracted, and it's just as if it were spinning and it were a little bar magnet, and it could be spinning this way or it can be spinning this way. And if it's spinning this way, let's say, then if the north pole is here for the external magnet, and it's going to get pushed down. If it's spinning this way, then it's going to get pulled up. That makes sense to you guys? I mean, it's not an actual, the electron isn't really this sphere of spinning electrical charge, but it sure acts that way if you're looking for this properties.
You're saying the polarity changes with the different rotation?
Yeah, if it's, it ends up, it only has two possibilities for which way it can rotate. One way or the other way. And if it's rotating one way, then the north pole's pointing perpendicular to its direction of spin, say up. If it's rotating the other way, the north pole's pointing down. So the polarity switches. Is that all right? Yeah. The right-hand rule will do the calculus. So the value the only thing that really matters to us with the spin quantum number is that it only has two values, and you'll see why when we talk about what's called the Pauli exclusion principle. There's a picture of there's a schematic of this experiment that these guys named Stern and Gerbach did that showed that electrons act this way. But basically that's what we need to know. Next. There's some pictures you probably should look at. They're on pages 83 and 84. And these are pictures of orbitals. That is, pictures of regions of space where there's a 90% probability of finding an electron in an atom.
That's not until the second exam.
And where these pictures come from is well, you can think about it as plotting what's called the radial probability distribution. And they have these graphs there too on page 83. You can think about the radial probability distribution as a plot of the probability of finding an electron as a function of the distance from the nucleus. Right? Basically multiplied by the position. And so for n equals 1, L equals 0. By the way, we designate this subshell as a 1s subshell. You see why? Because L equals 0, we said that means that that's an S subshell. And the 1 in front here means that tells you what ends. We have a 2s, a 3s, and 4s. And all that. For a 1s subshell, radial probability distribution function looks something like this. Again, you know, they have a more accurate picture. Figure 3.18, on the left-hand side, the bottom. And a couple of things to note about this is that, okay, so this is the nucleus right here, R equals 0. And this is going out away from the nucleus. But at the nucleus, when R equals 0, this goes to 0 also. You know, and that makes sense, right? Because you can't have an electron and a proton or a neutron in the exact same place at the same time, right? And then it increases to a maximum value at some distance from the nucleus, and then it starts decreasing again, right? Now, this line asymptotically approaches the x-axis. And what that means is that it never actually touches the x-axis until you get out to R equals infinity. So it approaches 0 as R goes to infinity. You guys okay with that? Really? I'll let that kind of stew in your head. Think about what that means.
It never touches X. It's just, well, I understand the fact that it doesn't never touch. Yeah, it never touches. Yeah, it's
They have,
always
like I
getting
said, they have
half,
more
half, half, half,
accurate
half, 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 half,
numbers,
but never getting to it.
There'll be a time
When n equals 2,
when you go to chemistry
you
lab.
guys have your books, it's probably just better to look at that.
All right.
Or, no, that's, okay, so I'll try to. When n equals 2, L equals 0.
Oh, it's gonna continue off that graph.
2s is subshell.
I'm gonna do a new graph.
Actually, like being in class with science.
Something like that.
Science? Fun? Never.
What are you saying?
A couple things to notice. What's that? It touches the x-axis.
Yeah.
A couple things to notice about the radial probability distribution function for a 2s subshell. And that is, first of all, there's 2 peaks, which means there's kind of 2 shells where there's a relatively high probability of finding the electron.
Your right-hand curve, is that asymptotically?
Yeah, they're all asymptotic. I got arrows.
What is acetone?
But 0 nucleus, peak, then it touches the axis, so it's actually 0 here. This is called a node.
What?
No.
Node.
And at a node, there's 0 probability of finding the electron.
Oh yeah, this was the purpose of this was.
Black space. And then it goes up again to another maximum, and then it asymptotically approaches 0. And you can do this, they do this for n equals 3, but I won't bother. If you were to
N equals 3 is crazy. So there's 2
look
nodes
at
in
the
N
black
equals 3.
curve, right?
Yeah,
The
3.
1s subshell.
3.
Yeah.
If you were to rotate that, I mean, it's not
I figured there was
about
one less
y-axis
node.
and
Use
the
your
x-axis at the
imagination.
same time, you essentially get a sphere. And that sphere is the shape of
It's like a
the
watermelon.
1s orbital. The 1s subshell. If you do the same thing for the 2s subshell,
Like a cherry.
you get a sphere out here, and then another sphere inside of here. So, the shape of any s orbital is a sphere. What distinguishes in a given atom an s orbital from another s orbital is that the higher n is for that s subshell, the farther out from the nucleus it extends, just like I said when I first described n. So when n equals 1, that, you know, with the 90% probability, that orbital goes out so far from the nucleus. When n equals 2, it's still a sphere, but now it goes out farther from the nucleus, and 3 goes farther, and so on. When we get to L equals 1, and you do the same sort of thing, you get the shapes of the p orbitals and the p subshells. They have pictures on the bottom of page 83. There's three different orientations here. With the s subshell, remember L equals 0. So m sub L equals 0 means there's only one orientation, one orbital in a given subshell. So there's only one shape. But when L equals 1, when it's a p subshell, there are three possible values for m sub L, -1, 0, and 1. And what that means is there are three different p orbitals in a given p subshell, because it has three values for m sub L. You guys following all this? When L equals 1, that's a p subshell. That's what we call a p subshell, right? And if you go back and look at the rules for m sub L, it's negative L through positive L. So if L is 1, m sub L is -1, 0, or 1. That means three values. That means three different orientations for a p orbital and a p subshell. It means there's three different p orbitals for a p subshell. And they have pictures of three of those on the bottom of page 83 there. They look kind of like
So these are all p
like a
orbitals.
spoon that's squeezed in the middle.
Look, see?
So that means
Big moves out at the end and it's narrow in the middle. The middle, that's a node, just like I described here.
It's probably
sub
a
L.
3.
You guys see
M
those?
sub L. So these three are
Those
when it
three
equals
different
1, 0,
2.
1.
p orbitals.
These three must be the 1 through.
They have
1 through
different
3. This is
orientations.
0, this is 1,
And if you
2,
impose a
3.
Cartesian coordinate system on
Okay.
them,
See how that's.
one of those orbitals would line up on the x-axis, or you can make it so that, if you do so, if you make it so that one of the orbitals lines up on the x-axis, another one will line up on the y-axis, and another on the z-axis. And so we call those three different p orbitals.
I feel very good about being confused.
It's
Yes.
coming back to me.
Y.
How come PZ is the same as GCP?
What do you mean? It's different. It's on a different axis, right?
Yeah.
Can you see that?
The z-axis. It's a three-dimensional.
Yeah. So yeah. You have to imagine this as a three-dimensional world.
What if you don't have a good imagination?
Then
What if
you're
you don't have a
perfect
good
for chemistry.
imagination? You can't imagine the
You can't
orbitals.
imagine three. You better stick
What? Can't you draw it for us?
No.
You can't.
Thank you, Joe.
I was wondering who was saying that.
Right. Next, L equals 2. B subshell. So L equals 2 means that m sub L can be -2, -1, 0, 1, or 2. That is 5 different values for m sub L when L equals 2. That means there's 5 different orientations, 5 different orbitals in a D subshell. They have pictures of those on page 84.
Why does the second one look so different than the other one?
It's its orientation, right? Yeah, you're right. The way they ordered them, the second one, is dz squared. It looks kind of like a p orbital with a donut around the middle.
Yeah.
Right, yeah. The other ones look like two p orbitals kind of oriented different directions, right?
And that's the same as
That's what it turns out. That's what Schrodinger's equation gave us, and it works. So
That's like a nuclear explosion. Look at that. She's in the sky looking down on that.
Look at this 1S thing. 1SP, 2SP.
So, I mean,
Is that an L? I'm pretty sure that's an L.
that's, yeah, L.
Be a stick figure. Equations.
if you look at those pictures, that dx, they do specifically the n equals 3, the 3D subshell. The dx squared minus y squared, again, if you impose the Cartesian coordinate system on this, the two lobes, okay, again, it kind of looks like two orbitals, 90 degrees to each other. The lobes are on the axes of the x and the x and y axes. The dz squared is up and down the z-axis, but it has that little donut in the middle. And then the dxy, those are, the lobes go between the axes and the xy plane. Can you see that? We'll look at the picture.
Yeah.
Yeah. Okay. And then the dx and z, those lobes go between the axes and the xz plane. And then the dyz,
Look, check it out.
the lobes go between
Yeah,
the
I
x
see
and
it.
y.
It's in between.
Yeah, I know, I see it.
See how that
I just
works?
want him to draw it.
The important thing really though, there are 5 different orbitals.
I remember last night I got so confused after he drew it. I was like, what is that?
It was a 6
When
picture.
is the,
Because the book had a horrible
okay, so,
Image.
examples.
Yeah, that last book was horrible.
One thing I liked with the last book was the tables.
what's the first
The tables were excellent.
value of n that will let us have a d subshell?
1.
Here's the rules. Let me condense the rules. Okay, before on the board, I wrote descriptions and the rules. Let me just put the rules. Okay?
Next value for L. -2, -1, 0, and +1, +2.
That's what he's talking about, right?
Well, there's 5 values. Shouldn't there be 5 values?
And it should be 2. It's 2.
Well, because it's 2
That's
negative.
right. Who said that? That's right. That's right. So,
You're like
d
2, 0,
subshell.
2,
Remember,
1,
that's
0, 1,
shorthand
2.
for L equals 2, right?
I told you.
So, when n equals 1, what values can L have?
2, -1, 0.
Only 0, right? Because it has to stop at 1 less than n.
Yeah,
See that?
that's what.
So when n so for an S subshell, you can have that at n equals 1 or higher. When n equals 2, what values can L have? 0 and 1, right? It goes up to 1.
Oh,
less,
0
right?
and 1, okay.
So it can have an S subshell and a
But it
D
can't have a
subshell,
nothing
but you
negative.
still can't have a D subshell. You guys see that? Because the
Uh-huh.
rule for L won't let us get that high yet.
Has to equal 2.
But now once we get to n equals 3, that distance from the nucleus, that's the first time where L is allowed to be equal to 2. That means the first time we're allowed to have a D subshell.
Hooray.
What's the first n that will allow us to have an F subshell?
4.
Or 4, one more, right? In a hydrogen atom with just one electron, the only thing that the energy of that electron depends upon is n. The only quantum number that determines the energy of that electron is n. Higher n is, the higher the energy. But once you start putting 2 or more electrons into an atom, they start interacting with each other. And now the energy of those electrons in the atom depends not only on n, but also on L.
Is that like hydrogen?
Yeah,
Like hydrogen.
like hydrogen. Like helium.
what I just said. So if it's a single electron atom, like hydrogen, then the higher the N is for that electron, the higher the energy of that electron. Multi-electron atoms, like most other neutral atoms, all of the neutral atoms, energy is dependent on N and L. So, and this is hierarchical. So in general, there are some exceptions we'll talk about, but the higher N is, the higher the energy of that electron. But within an N, okay, for a given N, the higher the value of L, the higher the energy. So what that means is that for a given N, in general, a D subshell is higher in energy than a P subshell, which is higher in energy than an S subshell, or an electron in this subshell. There's a mnemonic that I should probably show you now that lets you predict the relative energies of electrons in all the subshells and the atoms in the periodic table. The way you do this is we're going to write the subshells. All the subshells, S subshells will be in this column, and then all the P subshells in this column, and so on. So 1S, 2S, 3S, 4S.
I love this.
We're only going as far as we need to describe the atoms that we know in the periodic table.
The most
When we
workable
go to
is
this
4.
column, which is where the P subshells will be, is there a 1P subshell?
No.
No, because when
Oh, by the way, doing your
N
lab
equals 1,
right
L can only be 0.
Did you finish your lab right
L equals 1.
No.
So we have to start at 2.
We didn't have time.
Well, because it's close for the problem.
What? What'd you say? You talk smack.
And then when we get to
I
D,
just
the
wanted to
first
do
time
my
we see a
write-up
D
before.
subshell at N
I'll
equals
do it on
3.
Monday night.
I'm sorry.
It's cool, it's cool, it's no problem.
And then F starts at 4. And the relative energies of electrons in these subshells go like this. You start at the top right-hand corner, and you draw an arrow diagonally down to the bottom left.
Can it be 1P, 2P, 3P?
Nope, it's just 1S, 1S, and then 2S,
So you go through the 1S subshell first, and then you come back up, and then you go through the 2S. You guys, are you seeing what I'm doing?
Yeah,
Then you come back up,
it's
go
killing
through
the
the
SP
2P,
orbital.
and then the 3S. 3P, 4S.
What does that say?
3D, 4P, 5S. So I'm not gonna, it's gonna get messy if I keep going. You guys see how to continue from there? So what this tells us is that
Yeah.
the lowest energy subshell is the 1S. Next is the 2S, and then the 2P.
Oh,
So-
I see.
At the same end,
Mm-hmm.
the P subshell is higher energy than the S subshell. Higher L, higher P. After the 2P, then we go up to the next end, 3, to the 3S. We come next to the 3P. Then we hit 4S before we hit the 3D. And this is true, this is the way that it works. It ends up that an electron in a 4S subshell is lower in energy than an electron in a 3D subshell. 3D and 4P and 5S and so on. So, we are almost finished chapter 3. It's a big one. Next Tuesday, when we come back, we'll use this to start throwing electrons into atoms and get electron configuration. We'll finish chapter 3 easily.